Right, so in this second video I'm just going to go through a number of examples of integration to show you how it works in practice. So in the first video we saw that there were these two rules, integration by substitution and integration by parts, which follow from the product and chain rules of differentiation. So I'm going to start by looking at some examples of integration by substitution. Okay. So remember what the formula says. It's told you that the integral of f of x dx is equal to the integral of f of x of u. So if you introduce x as a function of some variable u, times the derivative dx by du, integral du. That was the formula, and if you want to make this a definite integral, then you need to put the limits of x, a and b here, and the limits of u, u of a, u of b here. Okay, so let me do some simple examples of this. So the first case I want to talk about, which is very important, is if you've got the integral of some function of ax plus b dx. So in this case it's clear what substitution you want to make. You want to say that u is equal to ax plus b, so therefore du by dx is just equal to a, and as I said, this is often written du over a equals dx. So we can substitute dx for du over a, and therefore this is equal to the integral of f of x of u, so that's f of u, times du over a, and because a is a constant you can take this out, this becomes 1 over a, the integral of f of u du. So let me show you some examples of this. The integral of 3x plus 1 squared dx. Okay, so here a is 3, so this is equal to a third the integral of u squared du. But you know that the integral of u squared is a third u cubed. So therefore this is 1/9 u cubed plus c. Okay, so here you will get c over 3, but because c is an arbitrary constant, you can just keep writing it as c. And then finally, if you put in what x was, what u was in terms of x, then this is 1 over 9, 3x plus 1 cubed plus c. Okay, so a couple more examples so you can get the pattern. What if I want to do the integral of sine 5x dx? So here a equals 5, so this is 1 over 5, the integral of sine u du. This was a basic integral, it's minus cos of u, so this is minus a fifth cos of u plus c. And then finally put back in what u is, which is 5x in this case. So you get minus 1 over 5 cos of 5x plus c. Okay, and hopefully you see the pattern, so I'll just do one more example like this. The integral of 1 over 2x minus 1 dx. So here a equals 2, so this gives you a half times the integral of 1 over u du, which is a half log of u plus c. And then finally put u back in terms of x. This is a half log 2x minus 1 plus c. So you can see in each of these cases the constant multiplying the x just is divided, the function is divided by that at the front. Okay, so here it's a third, here it's a fifth, here it's a half. Okay. Now I want to say something about this result here in a bit more detail. So if we consider the function f of x is 1 over 2x minus 1, then the graph of this function, it blows up at a half. Okay, and it goes like this and like this. you note that this log is only defined if x is greater than a half. So this one is only defined in this region here. Right? But the function itself is perfectly well defined if x is less than a half here. So although this answer only works in the region here, we ought to be able to find another answer which works in the region here. Okay. And indeed you can do this, and this relies on the fact that the indefinite integral is not unique, it's only defined up to a constant. Because if instead of taking the function log of 2x minus 1, I instead consider differentiating the function log of 1 minus 2x, so in other words, minus what you've got there, then you see this also works, because you get a half, then you differentiate this, that gives you 1 minus 2x, and multiply by the derivative of this, which is minus 2. Okay, and this is therefore minus 1 over 1 minus 2x, which is 1 over 2x minus 1. Okay, so therefore we can also write that the integral of 1 over 2x minus 1 dx is a half log of 1 minus 2x plus c. That is also correct. And this definition is the one that works in this interval here, when x is less than a half. Okay, so in general, you often write that 1 over 2x minus 1 dx is equal to a half times the log of the absolute value of 1 minus 2x plus c. And then this definition then works in both regions. As long as x is not equal to a half, you get a sensible number out of here. Okay. A second thing to note is if this was a definite integral, so if I asked you to give the definite integral between a and b of 1 over 2x minus 1 dx, then you have to be careful about where is a and b, because if a and b are both up here, that's no problem, it's just given by this function. If a and b are both down here, that again is no problem, it's just given by this function. However, if you try and do it from a, which is less than a half, up until b, which is more than a half, then this integral does not make sense, because basically the area, the definite integral, remember, is defined as the area. This area here is infinite, and this area here is also infinite. Okay, so the answer you get is infinity minus infinity, which in general is not well defined. So there is something known as the principal integral, which makes sense of expressions like this, where you get infinities, but I'm not going to talk about that now. Just to warn you that if you get a definite integral here, where the function blows up at some point, you have to make sure that that point is not inside the limits of the integration in order for it to be well defined. Okay, so sticking with integration by substitution, I want to give you one more example of where it's often used. So this is where you've got the integral of x times some function of ax squared plus b dx. Okay, you get quite a lot of integrals like this form as well, and here again it's not too difficult to guess that the substitution you want is ax squared plus b. Then du by dx is 2ax, which you can write as du over 2a equals x times dx. Okay, and you see that you've got x times dx here, so we can replace x times dx by du over 2a, and this therefore becomes the integral of f of u times du over 2a, and you can take the constant outside, so 1 over 2a, the integral of f of u du. So again, you have a much simpler integral here. So let me do some examples of this. Suppose that I want to do the integral of x times e to the x squared dx. Okay, so this is an integral of this form. Here, u is just x squared. Okay, so a equals 1 and b equals 0. So from this formula, this is 1 over 2 times the integral of f of u. So f is this function here, u is x squared, so this is e to the u du. Okay, and this integral of e to the u doesn't change, so it's this. And then finally you should put back u in terms of x, so you get half x squared plus c. Okay, so that one works. Here's another example. Integral of x over 1 plus x squared dx. So here again, u is equal to 1 plus x squared. So a is 1 and b is 1. So here you get 1 over 2a, that's a half. The integral. So f is the function here. So that's 1 over 1 plus x squared. That's 1 over u du, which is a half log of u plus c. And then if you put back in what is u, this gives you a half log 1 plus x squared plus c. Okay, should we just do one more example? Okay, the integral of x times the log of 2x minus 1. Oh wait, no, that's a bad choice. I'm going to explain how to do that integral later on, but not now. The integral of x times sine 2x squared minus 1 dx. Okay, so here u is 2x squared minus 1, so that means a is 2. So here I get 1 over 4, and the integral, so x dx, this is sine of u du, and the integral of sine is minus cos. And finally, put back in what u was, minus a quarter cos 2x squared minus 1 plus c. Okay, so that is all the examples I'm going to give you of integration by substitution. For this class, as I said, the hard part is guessing what the substitution AU should be. So in this class, all the examples I'm going to ask you are either going to be case 1 here or case 2 here, or I will explicitly tell you what substitution to use for you. So either they'll be like this, and you know what this, you should use this substitution, or they'll be like this, and you know you should use this substitution, or I will tell you what substitution to use for this class. Okay, now I did say at the start that you need to be a bit careful for doing the definite integrals. When you make a substitution, you have to change the values of the limits. So I just want to show you one more example with a definite integral, so you see how that works. Let's suppose I want to do the integral between 0 and 2 of x e to the x squared dx. Okay, so here it's the same thing as we've got here. So here it's half e to the u du, but we need to change the limits. U is equal to x squared, right? So if x is equal to 0, which is here, then that means that u is equal to 0. So this one stays 0. But if x is equal to 2, as it is here, then u is x squared, so u is equal to 4. So here I need to change the upper limit from 2 to 4. Okay? Then we've seen that this is e to the u times a half between 0 and 4. So this therefore is a half e to the 4 minus e to the 0. E to the 0 is 1, so this is a half e to the 4 minus 1. Okay, so just to show you, if you make a substitution, you have to change the limits of the integral as well, according to what the value of u is, not the value of x. Okay, so that's all I'm going to say about integration by substitution. So next we're going to look at a few examples of integration by parts.